Hello, in this video we are going to discuss the reactivity of carboxylic acid derivatives, and then we're going to discuss the overall mechanism that we're really going to cover the rest of this chapter, which is called nucleophilic acyl substitution. So let's start by ranking our carboxylic acid derivatives. So let's start with our acyl halide, and we'll just draw a chlorine there for the halide. Then we're going to draw the anhydride functional group, followed by an ester, and last but not least, an amide. And we could also put nitriles below that too, but we'll just list these four. And the main idea here is that reactivity is going to increase going up this list. So our most reactive derivative is the acyl halide, and our least reactive is the amide. Now, why is that? Why is the acyl halide more reactive than anhydrides or esters or amides? Well, it has to do with that leaving group. So let's list the leaving group. And we'll also highlight the leaving group as well. So on our acyl halide, that would be the chlorine or the halide. So that could also be bromine. On the anhydride, that would be one of the groups. It could be left or right, but we'll just highlight the one on the right. The next one, our ester, the leaving group is an alkoxide group. And on our amide, the leaving group is NH2. So let's write those down. Now remember, when these groups leave, they're going to take electrons with them too. So these will all be negatively charged. All right. So one way that we can think about these leaving groups related to reactivity is how stable are they? So let's look at the conjugate acids of these leaving groups, because that will help us kind of figure out how stable the leaving groups are on their own. So we're going to write the pKa of each conjugate acid, and then we can compare them. So the conjugate acid of a chloride ion is hydrochloric acid, and the pKa is -8. Now remember, the lower the pKa value, the more acidic the acid is. So here, hydrochloric acid, we know, is a really strong acid. So that tells us that its conjugate base, the chloride ion, is really stable, and that's what makes it a really good leaving group. Now, because we have a really good leaving group for our acyl halide, that means that the acyl halide is very reactive because its leaving group is super stable. So it's all connected. So let's go to the anhydride. So its leaving group is a carboxylate. So that's the conjugate base of a carboxylic acid. And remember, we said that the pKa of carboxylic acids is around 0 to 5, depending on what that R group is on the right. So carboxylic acids are also pretty acidic, which means that their conjugate bases are fairly stable. Not as stable as a chloride ion, but still fairly stable. So that means that anhydrides have a fairly good leaving group, and so they will be fairly reactive. Same with alkoxides, which is our next leaving group for the ester. So the conjugate acid of an alkoxide is an alcohol. And the pKa of alcohols is around 15, kind of in that range. Again, it kind of depends on that R group. So we'll do approximately 15 there. Now, alcohols are not as acidic as, for instance, hydrochloric acid or carboxylic acids. So that's going to make our ester slightly less reactive because it has a leaving group that's not quite as stable as these other ones we've talked about. And then finally, when we look at amides, the leaving group is NH2-, and the conjugate acid of that is ammonia. And we all know ammonia is a base, right? And the pKa of ammonia is 38. So ammonia is not acidic at all. Its pKa is really high. So that means that its conjugate base is not very stable. It's unstable. It would prefer to have another hydrogen there. So that means that the leaving group for amides is not stable. So amides are not very reactive. So just things to keep in mind as we go forward. And we're going to start going through each of these derivatives, how to prepare them, and their reactions that they can perform. But in general, all of these derivatives can undergo what's called nucleophilic acyl substitution. So let's talk about that. And we're just going to talk about it in generic terms, and then we'll kind of look at specific reactions. Now first, we're going to start by assuming that we have basic conditions for this substitution reaction. And then next, we'll talk about acidic conditions. All right, so let's say we have a carboxylic acid derivative. And that Z group, remember, is an electron withdrawing group. So that could be a chloride, that could be part of our anhydride, so that carboxylate group, it could be the alkoxide group, or the NH2 group that we saw, depending on which derivative you have. Now, if we have basic conditions, then our nucleophile will be negatively charged and ready to attack. So the first step involves that nucleophile attacking the carbonyl carbon, very similar to aldehydes and ketones, except here we have a leaving group. So once that nucleophile attacks, electrons are going to move up to oxygen, and we're going to create a tetrahedral intermediate. So our oxygen atom is negatively charged. We have that electron withdrawing group Z. We have our alkyl group and our nucleophile that just added into the carbonyl carbon there. Now, because we have a leaving group, what we can now do is reform that double bond between oxygen and carbon and kick out our electron withdrawing group, which is also our leaving group. And then finally, we get our new product. And then our leaving group will be negatively charged. So again, this is a tetrahedral intermediate, and that's really important here for the acyl substitution. So we're calling it substitution, and normally when we think about like SN2, everything happens at once in a concerted mechanism. But here you really do need to form that tetrahedral intermediate because that more accurately represents what's happening in the reaction. Now, this reaction is going to be faster or more favorable if that Z group is a good leaving group. So let's just make a note. So this reaction is more favorable if Z is a good leaving group. So again, going back to our reactivity chart, if Z is chlorine or bromine, then that's a very favorable reaction. If it's a carboxylate, then that's also pretty favorable. If the leaving group is an alkoxide, then it's not as favorable. And if we have an amino group there, then it's really not very favorable. It's going to be the least reactive. Okay, so what if we have acidic conditions instead of basic conditions? How would that affect our mechanism? So let's draw our carboxylic acid derivative. And we've got our nucleophile, which will probably be neutral in acidic conditions. And then we'll also have some acid floating around there, so some protons. So similar to our acidic conditions with aldehydes and ketones, here we have a carbonyl group again. So our oxygen atom on the carbonyl group for this derivative can grab onto a proton, and then we'll have a positively charged oxygen atom. Okay, so now our nucleophile will come in and attack the carbonyl carbon. We'll move electrons up to oxygen. And that's going to create our tetrahedral intermediate. Now this time our intermediate will look a little bit different since we're under acidic conditions. So instead of a negatively charged oxygen, we're going to have a neutral oxygen that's bonded to hydrogen. And then our nucleophile has a hydrogen attached, so it will be positively charged. So what we're going to do is remove the hydrogen on our nucleophile. So let's just highlight that so we know which hydrogen we're talking about. All right, and so now we have a neutral nucleophile. And in this next step, our oxygen atom can reform its double bond to carbon, and that's going to kick out our leaving group, Z. So that will give us a carbonyl group again. But oxygen still has that hydrogen attached, so it's still positively charged. So finally, we're going to remove the hydrogen on oxygen, and that will give us our final product. Okay, so we get the same product under acidic conditions, but the mechanism is just slightly different. So again, under basic conditions, the nucleophile will attack first. Under acidic conditions, the oxygen protonates itself first. So let's look at an actual reaction that involves nucleophilic acyl substitution. So the reaction we're going to talk about is called Fischer esterification. Kind of a long word there. And this is a reaction that we're going to see in a future lab, so in our synthesis project. All right, so we're going to start with the following. We have a benzene ring with a nitro group, meta to a carboxylic acid. And then we're going to use acidic conditions and an alcohol there to turn that carboxylic acid into an ester. So that's why it's called esterification. We're esterifying. I don't think that's a real word, but okay, so let's just highlight what happened here. So this carboxylic acid is turning into an ester. And the rest of the molecule stays the same. All right, so in the first step, as we said before, under acidic conditions, the oxygen atom on our carbonyl group is going to protonate itself. And you'll notice I'm drawing some equilibrium arrows there. But this will make our carbonyl oxygen positively charged. And then in the next step, our alcohol is going to come in and act as the nucleophile. So the oxygen atom is going to attack that carbonyl carbon, just like we saw before. And then we're going to end up with a tetrahedral intermediate. Okay, so we're going to have our alcohol. We'll have another alcohol because remember we have our carboxylic acid there. And then that oxygen from the alcohol, the methanol, is going to attach. Oh, my pen likes to go bold on me sometimes. There we go. Now, in this next step, we need to create a good leaving group because you'll notice up above we just have 2 alcohols, right? So that's a hydrate. So similar to our aldehyde and ketone chapter where we went over those mechanisms, we're going to transfer a proton from our methanol group over to one of the alcohols. I know methanol is an alcohol, but it's kind of hard to describe sometimes, but we're just going to move that highlighted hydrogen over to one of the alcohol groups up above. So we'll just write plus or minus a proton. Oops. Let's see, I got to draw my benzene ring first. There we go. All right, so now we have a good leaving group, which is our water group. So the oxygen on the other alcohol group can reform its double bond with the central carbon, and that will kick out our leaving group of water. Okay, so now we've reformed that carbonyl, although we still have a hydrogen attached to our oxygen. But now notice that we have almost have an ester there. We have OCH3 on the right-hand side instead of an OH group. So in this last step, we're just going to remove that proton from the positively charged oxygen, and that will give us our ester group on the benzene ring. All right, so we're going to perform more reactions like this one, this nucleophilic acyl substitution reaction. First, we're going to focus on acid halides, in particular acid chlorides. We're going to look at how to prepare them, and then we're going to go over the reactions that they perform, which are mostly these nucleophilic acyl substitution reactions. Then next week, we'll start going over the other carboxylic acid derivatives. So we'll talk about our anhydrides, our esters, and finally our amides. All right, so I will see you in the next video. Good luck.